How to create an artificial intelligence. In my last videos, I stated that AI is about transforming numbers into other numbers. I stand by that statement. Yet writing a prompt to ChatGPT does not feel like creating a set of numbers. And reading Cleverbot's answer does not feel like decrypting a set of numbers. It is the art of the AI scientist to reframe a problem into this number-to-number transformation. And since ChatGPT is all the rage at the moment, I thought I could try to show a small version of how an AI can process text. That will not be ChatGPT. I'm an image guy, so I would prefer to go more in depth with something else. For the experts out there, we will be talking about the unreasonable effectiveness of recurrent neural networks. So how can we reframe a prompt like "Dear ChatGPT, do you like ice cream?" Well, it seems a bit basic, but this prompt is constituted by letters. I can ask my computer what letters it can print. There are 100 letters that my computer can print. Look at the first of them. If I decide that this ordering of the letters is always the same, I can attribute a number to each letter. It is simply its position in the ordering of letters. We can replace letters by numbers. It is now time to use this incorporeal voice for exuberant exultation. Yay! Look, 0 stays 0, 1 stays 1, it becomes 10, and our prompt becomes that. Now AI scientists figured out with experience that AI has difficulties handling numbers of different magnitude. For example, 1 is a number of small magnitude, and 100 is a number that is 2 orders of magnitude bigger. But do not forget that AI live in computers, and computers are good at handling a lot of numbers. They always have been, all the way back to the time of the analytical engines of Charles Babbage and Ada Lovelace's programming. Thus, instead of giving one number big or small, we can give them 100 small numbers. And it turns out that computers handle that very well. Let's attribute 100 numbers to each letter. All those numbers are zeros. And in this list of zeros, I set the 1 at the position of the letter to 1. This is called one-hot positional embedding, and it's very important. For example, in this list of printable letters, the 0 will be 1000, etc. 2 will be 00100, etc. Coming back to the earlier prompt, "Dear ChatGPT, do you like ice cream?" The first step transforms a sequence of letters into a sequence of indices in the list. And this in the second step, the indices are transformed each into a one-hot encoded vector. Each column is a vector of zeros, and the number at the position is set to 1. This looks like a big hunk of numbers, but again, computers are good at handling this. My idea now is to feed column by column a number transformation machine that will give me an output. I will use a number transformation machine that is called an LSTM, with a linear output layer. Its insides look a bit like that. It's a bit confusing, but there are numerous online resources with better drawings and good explanations as to how this LSTM functions. For our purposes, an LSTM is a machine that takes vectors at the input and gets a vector at its output. We design the LSTM's training process in order for the output vector to be appropriate, meaning it prolongates the sequence of input vectors. Look, I put a vector at the entrance of the LSTM and it generates an output vector. Then I put this generated vector at the end of the sequence and I re-input the new sequence with the LSTM's answer to get a new answer. I did the 35 times to get a sequence of vector that would be the LSTM's answer to this all-important question that was our prompt. Afterwards, I translated from one-hot vectors back to letters. I got that. Only chevrons. This is absolutely bad. This is because I used an untrained LSTM with randomly initialized parameters inside of it. And this allows me to transition neatly to the ideas that come into training our LSTM. The languages we talk in are structured. That implies that the order in which we say words or the order in which letters appear in words is not random. That is how I can say, "Dear ChatGPT, do you like ice cream?" And that sounds like a real sentence that can be said. Compare with ChatGPT, "Ice do dear like cream you?" Those are the same words in a different order and they have lost all sort of meaning. The same is true for letters. Look at frequent words in English and try to guess what the next letter would be. TH can be followed by E. TH can be followed by T. And after the E of the and the last T of that, it is reasonable to expect a space character, but they are invisible and thus difficult to draw. But they are here, believe me. In order to get the model to copy sequences of letters that appear often in speech, I need a lot of speech as examples. I took the King James Version of the Bible from the Gutenberg Project. There are really a lot of sequences of letters in this book. Then I take randomly sequences of 25 letters. Why 25? I don't know. I tried with 25 and saw it worked well. If it had not worked, I could have tried another sequence length. So I translate those 25 letters into one hot vectors and feed them into the LSTM. And I get one vector as the output. I compare this output with the 26th letter of the sequence and change the parameters of the LSTM to minimize the difference between the LSTM's answer and the true letter. All this is done in the one hot embedded vector form, because that's where the LSTM is at ease. But when I have done this time several thousand times, I can see what the LSTM generates from our prompt. I get this. This does not resemble any reasonable answer I expected about robots liking ice creams. That answer tells us two things. The first is that the LSTM's answer depends on its training data. This is seen well in this answer text. A sequence of letters that seem to come often is LORD. So it is interesting in order to minimize the loss function to produce this sequence of letters. The other thing we can see is that this LSTM's answer looks nothing like sequences of letters related to ice cream. And while it looks a bit like English speech, it is definitively not English speech. This is because we considered a rather small model. There are things that are more powerful at text generation than LSTM, like for instance transformers. Or I could have trained several LSTMs. In this case, one on ice cream and the other on the Bible. And then I train a classifier to analyze the prompt, and based on its answer I choose which LSTM to use. A similar idea is to train the LSTM together with a classifier. The LSTM generates sequences, while the classifier tries to tell if the sequences are genuine or generated by the LSTM. If the LSTM can fool the classifier, the LSTM is good. Likewise, the one-hot embedding is easy to understand but not the most efficient way to embed letters or words into numbers. By the way, I could have trained on sequences of words instead of sequences of letters. There were about 470,000 entries in the dictionary. My laptop is not enough to train on that. And that's the key. I'm just a guy fooling around on his free time with one laptop. The big guns have entire teams with supercomputers doing that all day long. That helps their models being much better than mine. But I suspect they use several of the tricks I mentioned here. Hopefully, I could transmit a feeling of how text processing works. This is the end of this video. Thanks for watching. See you next time. Or stay for a message from the sponsor of this video. Me, I'm the sponsor of this video. Don't cook food with cleaning chemicals, or any other chemicals such as those used in laboratories. Substances like bleach or acetone are known to be poisonous. You can poison yourself with food only. So using these substances in cooking is likely to be bad. So don't do that. Bye now.